Welcome everybody to our next talk. It's the talk Wallet Fail. As you all know, when you have something valuable, you put it somewhere safe. But as we as hackers also know, there's no place that is really safe. And our three speakers, Thomas, Dimitri, and Josh, are now going to demonstrate in the next hour the art of completely breaking something apart. So please give a big round of applause for Thomas, Dimitri, and Josh, and have a lot of fun.
So just to start, I'm curious how many people here actually own cryptocurrency? Raise your hand. And how many of you store it on a hardware wallet? So we're very sorry to everyone who has their hand up. Okay, so it's not just me, it's me, Josh, and Thomas. So we're all hardware people. We do low-level hardware stuff in varying degrees. And we got into cryptocurrency, and so I can recommend to everyone sitting in this room, if you're a security person, there's not a lot of people doing security in cryptocurrency, as much as that's painful to hear. So yeah, I mean, a lot of this is based on reverse engineering. We love cryptocurrency. I mean, for us, crypto also stands for cryptography, not just cryptocurrency. But no offense to anyone with this talk. It's just something that it's a category that we looked at, and so the results kind of speak for themselves. And again, this wouldn't be possible alone, so we have a lot of people to thank. I'm not going to go through all of them individually. Just be known that we're thankful to everyone on this slide. So we started this about 6 months ago. So we wanted to take a look at cryptocurrency because we own some cryptocurrency ourselves, and we saw that everyone's using cryptocurrency wallets. It's more and more the thing that you do. So we started a group chat, as you do nowadays, and we have 50,000 messages now and 1,100 images, and I had my first, I had my son in the meantime as well. So it's a really long time that we spent looking at this, etc. Okay. So what do we want to achieve though? Because people don't give the kinds of attacks that you can actually perform against cryptocurrency wallets and of credit. So first attack is supply chain attacks, where you are able to manipulate the devices before they get to the end customer. Firmware vulnerabilities, where you find a vulnerability in the firmware and can somehow either infect or do something else with the device. Side channel attacks, of course, I think that's one of the more obvious ones that people are familiar with. And also chip level vulnerabilities. So we were able to find one of each of these, and so that's the talk. We're going to talk about each one of these individually. So, but first, what's a wallet, just in case you are not 100% familiar with them? So a wallet, and in general, cryptocurrency, how do you do this? It's just asymmetric cryptography. So you have a private key and a public key. The public key, basically, it gives you the address. You can derive the address from this. The address is nothing other than the public key of the wallet. And you have the private key, and you need this to send transactions, so to actually operate with the cryptocurrency. So the private key is what needs to be kept secret. The public key is something that everyone can know so that they can send cryptocurrency to you. But it kind of sucks to have separate for each cryptocurrency pair, or for each wallet, maybe you want multiple wallets. It sucks to generate a new cryptographic pair for each one of them. So the wonderful people behind Bitcoin have thought of something for this, and it's called BIP32, BIP44. And so what it is you have a cryptographic seed, and you can actually derive the accounts from a single seed. So you basically store one seed, and you're able to implement and do unlimited amount of wallets. Okay, so basically you do key derivation, you add some data, do key derivation, and you can have an unlimited amount of wallets while storing a single seed. And this is what you're using when you're using a hardware wallet. So, and of course, for each key derivation, there will be a new private key and a public key, but it'll be generated in a predictable manner, and you only need to store one secret seed. So you only have to store the seed. You can write it down, and that's the advantage. But it's difficult to write down because it's binary data. So come BIP39, which is what you're most used to, which is a format in which you can take that cryptographic seed, that binary data, and actually convert it to a set of dictionary words that you can then easily write down on a piece of paper and store it at your mother's house, or store half of it at your mother's house and half of it at your grandmother's house. And that way somebody would have to go into both houses simultaneously to get your words. So Yeah, so what's a hardware wallet? So we just talked about what's a wallet. So why do you even need a hardware wallet? Well, the problem is, of course, computers can get backdoored, have malware running on them, and this is what you want to prevent against. How do you do this? You have a secure device. You store your seeds externally. Usually this is a USB-connected device that you store your crypto on, and so you can trust this even if you can't trust your computer, is the idea. So what happens is the computer sends the transaction to the device. The device gets the transaction. It can actually confirm or deny the transaction. It also displays the transaction. So before you do any cryptographic signing, you can see, is that actually what I was doing, or was my computer owned, and is it initiating the transaction for me? So you sign the transaction, and also, the seed never leaves the transaction, but the hardware signs the transaction for you. You send it back to the computer, and the computer can actually take that and send it to the internet, okay? So that's the quick rundown of how how hardware wallets work. So the first thing that we looked at was supply chain attacks, which is where Josh is going to pick up. You have a mic.
Do I need to?
Oh, sorry. Yeah.
Okay. So the three big things I want to leave you with as we go through the supply chain attacks are stickers are for laptops. They are not for security. So we're going to be talking about stickers today. They're for laptop decorations. They're not for security. Supply chain attacks are easy to perform, but they're quite hard to perform at scale. And the last takeaway that I hope you leave you with is that the vendor's threat model may not actually be your threat model. So security stickers. So some of the wallet vendors are using them. I've seen them on other products. They seem to be quite popular. I have a friend and colleague named Joe Fitzpatrick. He also likes stickers. So the stickers that he makes are the same as you would find on a security product. They have holograms, they have unique serial numbers, and they leave you with that nice, warm, fuzzy security feeling. And so Joe makes some funny ones. You can get a FITS 140-2 proof sticker, so you don't have to pay all the money for the FIPS one, just get the FITS one. So the first device that I looked at was the Trezor 1, and so the Trezor 1 actually has 2 levels of protection on the packaging. There's the hologram sticker, and then the actual box is enclosed with an adhesive. So it's supposed to be that you actually have to rip open the box to get into it. But if you use a hot air gun or a hairdryer, it's actually quite easy to remove. And so if you see on the left there, that's the original package, and on the right, this is a box that I opened and put everything back into. And if you look closely, there is a little bit of gap there. The sticker has a little bit of break, but this was a first try, and it's pretty close. So trust me, taking a sticker off is not very hard. Now, if you remember this picture of the sticker, because we're going to come back to it. But for the vendor, this is actually a real problem. So Trezor did put a blog post out that one of the challenges they face is that they're facing counterfeiting of their devices. So this is from their blog post. They say, hey, we've noticed that there's counterfeit devices. You have to look at the stickers to see that they're legit. So I said, remember, I'll look at that sticker. So I bought that case about 1.5 years ago for my previous DefCon talk, and it's the same sticker that they're saying is fake here. So then on their wiki, it's very confusing because there's 3 sets of stickers. So basically, yeah, stickers are very confusing. They cause problems for end users, and I was not even sure if I bought a real Trezor or a clone one. So this morning, I got out a new case, and just to make sure, I took off the sticker using very sophisticated equipment, including a very expensive Dyson hairdryer that was included in the Airbnb, and I was able to remove the sticker. So it comes off without any zero residue. So yes, stickers do not provide any security. On the Trezor T, they switched it from the box, so now the box can be opened easily, but now there's a sticker on the USB-C port. Again, as you would expect, you use hot air and you can easily remove it. Pro tip, don't set the hot air rework that high. I had it set for lead-free reworking, and I actually melted the enclosure. So if you're going to do this kind of supply chain attack, maybe set the heat a little lower. But if you just Google how to remove stickers, the same attack methods work. So this causes a bit of confusion because the Ledger device has a very, I will say, in-your-face piece of paper when you open the box that says there are no stickers in this box. However, I combed through about 250 one-star Amazon reviews, and a lot of them have to do with confusion about the stickers. So some of them are actually quite funny. So this one started out note to wallet hacker, so I was really into this. So I was like, okay, pro tip, what's this guy have to say? And basically, he was complaining that there's fingerprints on the device, so that's how he knew it was hacked. Another one complained that the fingerprints were on the wallet and was a hair underneath. So if you're doing supply chain attacks, be sure to remove any evidence via fingerprints or hairs. So anyway, stickers don't work. That's all I want to say about that. Once you get through this enclosure, though, you then have to have the challenge of actually opening the enclosure. These are 3 different wallet devices, Ledger Nano on the left, the Trezor 1, and the Trezor T on the bottom, all of which actually open pretty easily. So the Trezor 1, even, so this, I'm still not sure if that's the counterfeit or the real one, but again, on the real one today, I was able to pop open the enclosure. So it is ultrasonically welded, but you can pry it in there and open it. The Ledger Nano opens very easily, like without any equipment. But once you do this, what do you do once it's opened? So the attack basically is you take the microcontroller and you rework it. So you remove the microcontroller from the printed circuit board and you put on a new one that you bought from a distributor. Once you've done that on the Trezor devices, you can put your compromised bootloader on there. So I did not go as far to make the compromised bootloader, but I did confirm that once I switch the microcontroller, I can connect with a debugger over SWD, and I have free access to the chip. So some of the parts got blown off when I was reworking, but the STM runs fine. So yeah, so you just rework, reflash, and then you put everything back together. So next I want to talk about hardware implants. So you may remember the story that came out. There was this big hack by Bloomberg about hardware implants. I wanted to make a hardware implant. I also wanted to have a little bit of fun with this. So we are in honor of the Bloomberg story, which has some, may have some issues with it. We're about to talk about the Bloomburglar, which is a super micro fun implant. So the goals for this implant is I wanted this implant to happen after receipt. So it's both a supply chain attack and a physical one. Like a red team can perform this, a malicious insider could also perform this attack. 0 firmware, because more fun. It has to fit inside of a hardware wallet, so it has to be small. It has to also bypass a core security function, otherwise it's not an implant. Very few components. I have 1,000 of them with me, so I wanted to be able to, for the makers and the DIYers to participate in the hardware implant fun. So, what kind of implant did I end up with? Well, I decided to do basically an RF triggered switch. And so the idea is on these devices, there's a button, and the button is the last line of defense. So all the vendors assume that the host is going to be compromised. They just assume that's going to be easy because that's software. And so once you have a compromised host, you have to send it to the device, and then the human, so humans are still needed, humans have to look at it and say, is this the right transaction or not? They have to say yes or no. So now with this implant, through RF, I can trigger the yes button. So a human is not required to send transactions, I can remotely trigger it. Basically the RF comes in through the antenna, it goes through a single transistor, which is the main component, and it pulls the button low. And I'm sorry to say that the bill of materials is quite expensive at $3.16. $2.61 of that is this potentiometer I had to use, so it's a little bit expensive, I'm sorry. Also, why is this so big? I mean, this is an American dime, I can fit 2 on them. What's the deal? Why is it so big? Well, I optimized it for hand assembly, so it would be more fun to use. But you basically put the antenna in, and then there's an out button, and like I said, I have 1,000 with me. So just for scale, this is how it fits on the Ledger Nano, this is how it fits on the Trezor. It is also, because breadboard friendly is a thing, so we made it breadboard friendly. So you can also play along very easily at home. So then the last challenge with an RF implant is how do you design an antenna to fit in there? And so the big thing there with an SMA connector is the first prototype I did. Experimented with a few antenna designs, but remember it all has to fit inside the Ledger. So that's actually quite easy because the Ledger Nano has plenty of room to insert extra circuitry. And so it quite fits easily in the Ledger Nano. And then, so I did the implant, and then I started to go through the wallet process. I got to a check that said, is the Ledger device genuine? And here I actually got a little bit nervous because it wasn't working. And so it wasn't working. I was like, oh, maybe they're checking this. How do they detect it? Don't worry, it was only Linux. So it just doesn't work on Linux. So that was no problem. I did this on Windows, and no problems. The device is genuine. I was able to move on. So the thing is, this is a very crude receiver, but the attacker can always use more power. So here this is my antenna set up in the basement, and with a 50-watt transmitter, I could remotely trigger the button at 11 meters. And at this point, I'm just limited by my basement size. I'm very confident that I'd be able to remotely trigger this thing further. Yeah. So here we're going to see a demo of what it looks like. And so the other problem you have with hardware implants is how do you know you have the implanted device? So you have to label it some way. Ledger has this kind of Latin phrase that scrolls. I wanted my own Latin phrase, and so this is how I know this is my implanted device. So what you're going to see is that the transaction screen is going to show up. I'm basically going to trigger this remotely. So I'm going to show the radio come in, and then it's going to approve the transaction without any hands. So this is the transaction. There's the screen going. This is what you're supposed to verify. There's the radio coming in, 433 megahertz. And then it's going to proceed to the next screen without me touching the button. There you go. So this is remotely triggered, and that would have sent a transaction. So if you think about the context of you have a malicious software implant that sent it to a wrong address, the attacker now can remotely accept that and bypass the security module. So yeah, on the recaps, stickers are for laptops, not for security. Supply chain tags are very easy to do at a hardware level, but they're quite hard to do at scale. And when the vendor says that the device is genuine, that may mean different things. So.
Yeah, to segue to the next part. So 6 months ago, Josh Danko said something that I found kind of funny, and it's almost correct. If you put funny constants in your code, they will end up on DefCon slides, and they won't be laughing with you. Small mistake, they won't end up at DefCon, they will be at CCC. And so introducing the food babe vulnerability. It's a bootloader vulnerability in the Ledger Nano S. We did not come up with this constant. It's literally in the code, as we'll see later. So the name was not ours, but we like it. So we also bought the domain foodbay.be. The Ledger Nano S is a very simple wallet. It simply has a small display, it has a USB port, and 2 buttons. That's really all there is. And if you take it apart, you see it's just some pieces of plastic, the display, and the PCB. And looking at the PCB, it kind of has an interesting architecture where you have an STM32, which is just a general purpose microcontroller, and an ST31, which is a secure element that is, for example, used in pay TV and so on, and is regarded as a very high security chip, basically. And if you turn the PCB around, you see that they were nice enough to leave the programming port for the STM32 open to us, enabled. And this has been suspected by other people. We verified it. But, you know, you have to go through it. And obviously, Ledger is aware of this. And so let's look at the security model that the Ledger Nano S has. The basic idea is that if we look at this device, we kind of have this schematic of the STM32 being on the left and the ST31 on the right. And as you can see, all peripherals are connected to the STM32. That is because the ST31 does not have enough pins to connect peripherals. It literally only has a 1-pin interface, which is for the smart card protocols, basically. And so all the heavy lifting is done by the STM32. And Ledger splits this up into the unsecure part and the secure part. And the idea is that the STM32 acts as a proxy. So it's basically the hardware driver for the button, for the display, for the USB, similar to a North bridge in your standard computer. And when you take a computer and want to make a transaction, you create your transaction on the computer. It goes through USB to the STM32, and the STM32 then forwards it to the ST31. The ST31 then says, oh, a new transaction. I want to ask the user to confirm it. So it sends a display command to the STM32, which in turn displays it on the screen. And then you press the yes button. Again, it goes the same route to the ST31, which then internally signs the transaction. So the seed never leaves the device. And our signed transaction goes back through the STM, through USB to the computer. To us, this means if this chip is compromised, we can send malicious transactions to the ST31 and confirm them ourselves. Or we can even go and show a different transaction on the screen than we're actually sending to the ST31. And Ledger is aware of this, and we'll talk about how they try to mitigate this later. But first, we had to find an exploit, because while we do have debugging access to the chip, hardware access is sometimes kind of buggy, no offense. So we wanted to have a software bug, and so we started reverse engineering the firmware upgrade process. And when you look at the bootloader for the Ledger used to be open source, and back then they didn't have any verification of the firmware. So if you could basically boot the device into bootloader mode, flash whatever firmware you want, and then it would run it. After someone, Salim in this case, wrote about this, they changed it, and they changed it to do some cryptographic measure, and we were too lazy to reverse engineer that cryptographic measure because it's very time consuming, very hard. So we looked more at the parts surrounding it and how we can maybe find a bug in the bootloader to break it. And it turns out that when you try to upgrade your Ledger, it accepts 4 different commands. One is select segment, which allows you to select the address space at which your firmware will be flashed. One is the load command, which allows you to write data to flash. Then you have the flush command, which is basically like fsync on Linux and writes your changes to the non-volatile memory. And you have the boot command, which verifies the flashed code and starts booting it. So to us, the boot command is the most interesting because it provides all the verification and attempts to ensure that no malicious image is booted. And it turns out that if you issue the boot command, it compares the whole image to whatever cryptographical function they use. And if it's successfully verified, they write a constant to the address 0x8003000. And that constant is foodbabe. And so to not have to verify the entire flash on each boot, they just do this once, so only after a firmware upgrade. So basically, if you boot up the Ledger, it boots, it waits 500 milliseconds, it checks if you have a button pressed. If yes, it goes to bootloader. Otherwise, it loads the constant at 0x8003000, and if it's foodbabe, it boots the firmware. So our goal is to write foodbabe to that address. First attempt, we just issue a select segment command to exactly that address. We just write foodbabe to it, flush, and reset the device. Didn't work, unfortunately. So we had to do more reverse engineering. And it turns out that they use an interesting approach to ensure that you don't accidentally flash over the bootloader. So they basically blacklist a whole memory region. So if you try to flash from 0x800 4x0 up to 0x8003000, it returns an error. If you try to directly write to foodbabe, they thought about it and they have a very specific code path to prevent that. So they memset it to 0 and you're screwed again. And then finally it writes assuming you didn't error out. But it turns out that the STM32 has kind of an interesting memory map. And on a lot of chips, you can not only map your flash to one address, but you can also have it mapped to another address. And in this case, the flash is indeed also mapped to the address 0. And so the bootloader uses a blacklisting approach, so it only excludes certain memory areas. But it doesn't use whitelisting, where you could only explicitly write to this memory region. So they do not like writing to 0x0. Profit, second attempt. We just select the segment at 3000, which maps to 0x8003000. We write foodbabe to it. We flush, reset, and we can flush custom firmware. Awesome. So what do you do when you have a device where the display is not big enough to run Doom with a custom firmware? So in this case, it's an original Ledger. Press the button, put it into bootloader mode, which is part of the normal operation, and if you want to play a bit of Snake, come by later. So how are they protecting against this? I've mentioned before, Ledger is aware that you can reflash this STM32, and they put in some measures to prevent you doing malicious stuff. And basically what they do, and this is very simplified, and we did not bother to fully reverse engineer it because we didn't need to, basically. When the chip boots, it sends its entire firmware to the ST31, which then performs some kind of hashing or so, verifies that the firmware is authentic, and it also measures the time it takes to send the firmware. This is to prevent you from just running a compression algorithm on the STM32 and send it very slowly. How do we bypass this? So our idea was, because we don't only have flash, we also have RAM. So what if we create a compromised and compressed firmware that copies itself to RAM, we jump to it, and then it writes its entire compressed firmware to flash, uncompressed in that case, and then we just call the original code on the secure element. It will verify the firmware, it will run with the real timing, and boots up regularly. And so we attempted this. It took quite a while to achieve, because basically you can't do zip, you can't do LZMA, because even if you compress the image, you don't have enough space for a complex compressor. So our attempt was to find duplicate bytes, squeeze them together, and make space for our custom payload. And basically, we just have a table that says, OK, now you will have 6 zeros or something, and each table entry only takes a single byte. And it's only like 10 instructions in a sampler to run this decompressor. So you don't have a large code base. It's very easy to use. And it turns out that even with a very simple detector, like in this case, we run the script to find the longest duplicate data. And you can see on the first try, we get like 260 bytes of space for our payload, which is enough for a lot of things, let's say. And we have a working proof of concept of this, and we would go into a lot of details, but we only got an hour. And so we will release after this talk a non-offensive example of this that you can look at. How does it work? What can you do even if your firmware is attempting to be verified? And we also, and this is very exciting, we are working with the YouTuber Live Overflow, and he created a 20-minute video on walking through this entire food babe vulnerability, how the verification works, and how to bypass it to a certain degree. We don't want to weaponize it, so we will not release the full thing, but yeah, very excited for this. Stay tuned on our Twitter, and we'll link it for sure. As part of this, we also have a lot of software that we will release. So public release, we'll release the Snake firmware. So hopefully this evening you'll be able to play Snake on your ledger. If you bought some Bitcoin at 20,000 and now are bankrupt, you can at least play Snake. We will open source the compressor and the extractor. We built a logic analyzer plugin for the smart card protocol, and we built software that analyzes the communication between the STM32 and the ST31 on the ledger-specific data, and you can just dump it. So if you guys are interested in, for example, trying to break into the ST31, please have a go. And Ledger has a second device, which is called the Ledger Blue. We assume the reason it's called the Ledger Blue is because it contains Bluetooth, but they never enabled Bluetooth, so it's basically just a regular ledger with a color display and a big battery in it. And we call this part Fantastic Signals and How to Find Them. Because when we open up this device and we were chatting, we have this nice Telegram chat room where we are chatting 24/7 while doing this. And we open up the device, and the first thing, like literally 5 minutes after opening it, I saw that you have the secure element on the left and the STM32 on the right. You have some other stuff like the Bluetooth module and so on. The trace between the secure element and the microcontroller is pretty long and contains a pretty fast signal. So what is a long conductor with a fast changing current? Anyone got a clue? Correct. It's an antenna. So I pulled out my HackRF software-defined radio. This is just a more sophisticated RTL SDR, so you can just sniff arbitrary signals with it. I got a random shitty telescope antenna on Amazon, and I have my Ledger Blue. And so on this screen, you can see the blue thing is the radio spectrum around 169 megahertz. And if we start entering our pin, we can see that there's a weak signal. You guys see where this is going on the radio. Unfortunately, that signal is pretty weak. Luckily, they included an antenna. They call it a USB cable, but I'm not so sure about it. So this time with USB connected, and we do the same thing again, you can see like crazy radio spikes. And this is right next to each other, but even if you go a couple of meters, I was limited, as Josh, by my living room space, you get a couple of meters of decent reception. So our goal was to find out what is this signal. And if we just look at the recorded amplitude of the signal, we get this. And if you do a lot of probing and so on, you immediately see, okay, there are spikes. And there are 11 of them, and then there's a pause, and then there's more spikes. So this is probably some kind of protocol that first sends 11 bytes of data, then pauses, and then sends more data. So we looked at the back of the device, started probing every single connection, and tried to figure out, is this the CQ element, is this whatever, and it turned out to be the display bus. So we can sniff information on what is sent to the display remotely. And if we look at the signal that gets sent in blue, is the signal that gets sent when you press the letter 0 on the pin pad, and in orange when you press the letter 7. So we can see a very clear difference at certain points on the signal, which confirmed our suspicion. But building software for this is kind of boring. Like, digital signal processing is not really my thing. So what do we do? And we wanted to increase the buzzword load in our talk a bit, and so we are hacking blockchain IoT devices using artificial intelligence in the cloud. So our idea was, we record training signals, we use some kind of pre-filtering, we train an AI on it, profit, literally. Problem is, getting training data really sucks, because you don't want to sit there for 10 hours pressing the same key on a pin pad. It really doesn't sound like fun, and so this needs automation. So we took an Arduino, we took a roll of masking tape, a piece of acrylic glass, a PCB vise, and this is a Huawei pen for the extra amount of Chinese backdoor. And we let this run for a couple of hours. And you can actually see that every time it presses down, you can see that the digit that you pressed is highlighted. And the difference in the signal we saw earlier is probably the x and y coordinate of where it highlights the button, and that's the difference we can see in the trace. And so we had a lot of recorded data now. We created a training set, we created a test set, pre-processing, TensorFlow, AI model. It's really easy, surprisingly. And we tried our test set, did a prediction, and so the big question, how accurate is it? And it turns out, so this is the result of a cut of the test set. And if we zoom in on this, this basically tells you, we have the signal, this gray thing is just a picture representation of the signal, and it tells you how sure it is what digit it is. In this case, it's 7 with 98% likelihood, so pretty good. In our test set, we only have one wrong result, and overall we get around 90% accuracy. And to move this in the cloud, we are hosting this on the Google Cloud as the Ledger AI for you guys to play with, and we'll publish it online with a limited data set that is trained on a very close base. So you cannot do something super malicious with it, but it's nice to play around and see how this was done. And this brings us to the next part. Glitch me if you can. Thank you.
So now we're going to talk about the silicon level vulnerability with glitching attacks, fault injection. So to review, we'll be talking about the Trezor 1. And so I just want to go over very quickly what the architecture is of the Trezor 1 and some previous work that was done. So the Trezor 1 is quite a simple embedded device. It consists of only a few components. It has a OLED display, it has some buttons, and has a USB connector that are all externally facing. Internally, it has its main brain, if you will, is the STM32F205 microcontroller, which controls all the other operations on the Trezor, the display, the USB, and the two buttons. So last year, we gave a talk at DefCon, breaking Bitcoin hardware wallets. Here, we used the chip whisperer to mainly do the glitching attacks. The conclusions from last year is that the F205 was vulnerable to fault injection, but it was inconclusive if we could do a exploit via the fault. So this year we have a different result, but the output of that work was this board, what's called the Breaking Bitcoin board. Basically, it was a Trezor clone that just made it easy to attach wires and probes. And so we made this board. The design schematics are all online. That's open source hardware. Now, this is the chip whisperer setup that we were using. So we made the board specifically to fit on the chip whisperer target board. And this is just what it looks like when you use the chip whisperer GUI to perform a glitch. And here we were doing application level code, so it was very different. But I gave that talk, and then I met Dimitri and Thomas.
Yeah, so fortunately, we had Josh to do the talk last year and to kind of exhaust a lot of the firmware vulnerabilities that, or actually hardware vulnerabilities in the firmware that might have been there. So we immediately knew that we could exclude this. And so you can start looking at the underlying microcontroller. So in this case, it's the STM32 microcontroller that they use inside of it, and it controls everything. So compromising the STM32 microcontroller means that you can compromise the device. So so there's a couple of papers that have covered some of the vulnerabilities in the STM32. Specifically, there's one which describes a UV attack, which lets you downgrade the security on the STM32s. So we determined that paper, unfortunately, does not apply to our result because the Trezor is smart enough when it boots to check the value stored in flash, and if it has been altered in any way, to set it correctly. So they actually even protect it against this kind of attack. But nevertheless, you can see that there's some vulnerabilities. So there's another paper which unfortunately has not been published yet, and we couldn't get in touch with the authors yet, that should be coming out in January, hopefully, which describes glitches against the STM32F1 and the STM32F3. So now we have the F0, the F1, and the F3. And so basically, here's the product matrix. So 3 of them are already vulnerable. But we're looking at the STM32F2 and potentially the STM32F4 if we're talking about the Trezor Model T. So those we do not have vulnerabilities for yet. So let's take a look at how it works really quickly. So the way that STM implements security on the STM32 is that they store an option byte. And the option byte, the thing to remember is on a Cortex M3 or M4 microcontroller, that you don't have anything other than flash. So even though they call it option byte or refer to this as fusing or being permanent in hardware, it's still stored in flash, just like the user application is stored in flash. So it's the exact same non-volatile memory that's otherwise used. So basically, when you get a new STM32, it's shipped in a state where you have full access. So that's how Josh was able to rework a board and flash it with new firmware. And there's the ultimate security is what's called RDP2. So there you have no access. But you can see that basically if you have a value other than AA or CC, which correspond to RDP0 and RDP2 respectively, then you have what's called RDP1. And this is interesting because it doesn't give you access to the flash, which is actually where the cryptographic seed is stored on the Trezor, but it gives you access to RAM, it gives you access to the registers, but it doesn't give you flash access, like I said, and it doesn't even give you single stepping as well. So connecting a debugger in this mode will actually cause the hardware to hard fault, which we'll see in a second. So basically what we want to try to do is to downgrade RDP2, which is what the Trezor is set to, and we want to be able to access the device at RDP1, which is a somewhat vulnerable state. So I should say that this is the correct way to approach this, and it's great for doing an educational talk. But in all honesty, there's 3 of us, and so we did this completely in the dark over 3 months, trying different parameters on our glitch setups, which I'll show later. And we're able to find this, but I'm here to explain it to all of you so that it's easy to reproduce. So if you actually watch the STM32F2 boot, you'll see that it's relatively slow, and it's only this slow after you power cycle the board. So it takes approximately 1.8 milliseconds to boot, which is in microcontroller terms pretty slow. So you can see there's the power supply, there's the I/O pin, and that's approximately how long it takes to boot the firmware. So you can see that's where the I/O actually toggles, so 1.8 milliseconds later. So we just wrote some firmware to basically toggle one of the pins, measured it with an oscilloscope. Now we have the timing of how long that takes. So that's not super interesting because that's not really a trigger. And each one of these microcontrollers, internally, it has a boot ROM. So it has some ROM, read-only memory, right? It's not non-volatile memory. It's not the flash. It's literally a ROM, which is inside the chip itself. It's hard-coded. It cannot be fixed or patched. That gets executed first. So we wanted to actually attack that because anything else is the user application, and that's what Josh did last year. So you can kind of start to fiddle this down. So you see that 1.4 milliseconds of the reboot, nothing actually happens because this is now the reset line, and so the reset line goes high after 1.4 milliseconds. So you can ignore the first 1.4 milliseconds after you cycle the power. So now the next step that you can actually do is you can connect what's called a shunt resistor. So in the so oscilloscopes are there to measure voltage, and so you want to actually measure current to be able to know how much power consumption, how much power is being consumed by the device. So you do what's called a shunt measurement, and that's what I have on this slide right here. So you have the blue signal is now actually the power consumption, and so now you can actually look and see what's happening. So the first thing that happens is we have the execution of the boot ROM. So you can see in the power consumption curve, you can clearly see this moment in time. Then you have basically where the flash and option bytes actually get read somewhat, at least within the boot ROM. And finally, the third distinctive moment in time is where the application actually begins to execute. So now we've taken this 1.8 milliseconds, which is a relatively long time, and reduced it to 200 microseconds that we're actually interested in. And not only that, we know that we're actually interested in having slightly higher power consumption than the normal execution of the bootloader, or of the boot ROM rather. And this is somewhere between, let's say, 170 microseconds and 200 microseconds. So this is the time at which we actually need to glitch. And this is also reasonable parameters if you're trying to reproduce this at home. So what do you need to reproduce this thing? So the greatest thing that came out in the last couple of years is these cheap Chinese power supplies, where you take a cheap, old wall wart from one of your old Linksys routers, you plug it in, and then you actually have a controllable power supply with voltage and current, and you can adjust this and control this. And so that's what we're using here. The second thing that I have to actually control the timing is an FPGA. I use FPGAs for everything, and this is something that was easiest to put together with an FPGA because FPGAs have constant timing. So finally, we have a multiplexer there as well, and the multiplexer is actually switching between 2 voltages, between ground, so completely cutting the voltage off, and the normal operating voltage of the microcontroller. And finally, we have a debugger, the J-Link, which is highly advised if you want to ever do JTAG stuff. So it's just a JTAG debugger, and basically what happens is you let this run for a while, and it looks like this. It's not really super eventful. So you can see that the voltage, the yellow signal is actually the voltage, and you can see we're just dipping the voltage at different points in time, and simultaneously we have a Python script checking if we have JTAG access or not. And so pro tip to all the new dads, if you do this at home, you can turn your oscilloscope towards the door so that when you get up at night because the baby's crying, you can see if it's still running or not. So it's highly advised. So now Thomas is going to tell us how to get the seed into RAM.
Yes. So we had this thing running for 3 months roughly across 3 continents because Josh is in America, Dimitri is in Russia, and I'm in Germany. And so it took us 3 months to get a successful glitch. And even then we didn't believe it at first because we exhausted everything basically. And the only reason we finally got it working is that we did a mistake where we mistook 70 microseconds with 170 microseconds and had it run for a longer time. And that's how we found out that the boot ROM is actually super slow to boot on this device. And so once we had this downgrade from RDP2 to RDP1, we were able to read the RAM, but we cannot read the flash, which actually contains the seed. And so how do we find this? And our idea was we start reviewing the upgrade procedure, because on the Trezor, the way the bootloader works is it doesn't require your pin or anything to upgrade the firmware, which makes sense because let's say you have a bug in the pin function, you want to somehow be able to get rid of it, right? And the other thing is if you flash a fully valid firmware, it retains the data, it retains your seed. If you flash a non-genuine one, it actually will erase your seed and so on. And they do a really good job on the firmware verification. We reviewed it for days and days and days and didn't find anything. But so how does this upgrade procedure work? How is the seed retained? And so when you review the relevant code, you see that there's a call to backup metadata, which sounds like it's going to retain somehow your data. And indeed, you can see that it's literally a mem copy from the data on flash we're interested in into RAM. And so our basic procedure was we go into bootloader, we start a firmware upgrade, and we stop it before the RAM gets cleared. Because if you finish the upgrade procedure, the Trezor actually clears its memory again, which is a very decent way to do it. But we found a way to retain it in RAM. So it turns out that when you start the firmware upgrade process, it eventually asks you to verify the checksum of what you just flashed. And it turns out that at this point in time, the seed is still in RAM, and we can read it out via RDP2. And this is relatively simple to do once you actually manage to glitch the device. You basically just run OpenOCD dump image, you get an image of the SRAM, and you have the whole RAM contents. And so how?
So what are we going to do, Tom? Oh. What are we going to do, Thomas? What high-tech hacking tool will we be using today to extract the seed?
So we actually, before we were successful, we had hours of talks on how is the seed stored and so on. But we found this super sophisticated seed extraction tool that only runs on POSIX and POSIX-like systems. It's called Strings. And so basically, it turns out that when you have a firmware dump, if you have a RAM dump, as we do now, and we just run strings on the dump, we get a couple of really nice words. And I don't know if you remember the intro, but this is your seed. And you might be wondering what this little number is. This is your pin to the device. That was a great day. And so Josh, or one of Josh's employees, took all this mess we created on our desks and made it into this nice device, which is basically a socket where you put in your chip, and then we can read out the seed and so on.
Yeah, and so all of this stuff, including the board design, the FPGA code, so the Verilog code that we used, I mean, if somebody wants to, they can apply it and do the same thing with one of the ice sticks or one of the more open source friendly FPGA boards. This just happens to be the one that we all had lying around and could reproduce the work with. You can go ahead and do it. I mean, we suspect, I think Thomas said, we suspect you might be able to do it with an Arduino as well, because the actual glitch pulse is only approximately 60 microseconds, or sorry, six microseconds in time. So it's a relatively slow signal as well. So it should be relatively repeatable, even with something cheaper than this. But this is a way to automate this even better and to not have dangling wires or any of the small soldering that was required to do it in situ in the device, which we had on the previous slides.
Yep.
So all of that we're going to have on GitHub. And so I think the final thing.
One more thing before we are sorry. One more thing. So this breaks a lot of the Trezor security, but there is a way to protect your seed against this. So if you use a passphrase on your device, the way we understood it, it basically doesn't allow somebody with hardware access to steal all your funds. So if you add a passphrase to your Trezor, a good passphrase, and your machine is not already owned, you can somewhat protect against this. But a lot of people don't, so we are really sorry. We didn't mean any harm.
So, I mean, yeah, that's the conclusion. I would say so. So yeah, I mean, so all this stuff we're going to put online. I guess I said so you can follow us for the links online. So wallet.fail, it's a domain name. Believe it or not, fail is a TLD. So you can go to github.com wallet.fail, twitter.com walletfail. You can follow me, Thomas, and Josh on Twitter as well. And like I said, we'll be releasing all this stuff, so it'll go up slowly, just because I think when we set out 6 months ago, we did not expect us to have 100% success in everything that we were planning to do. So that's a first for me, at the very least.
The saddest part is that we have more vulnerabilities to other wallets, but only 1 hour. And so we also have some stuff to give out. So we have the hardware implant PCBs. We have 1,000 of them if you want to get some.
Talk to Josh.
Yeah. We even have components for them for like 100 devices. So hit us up and we can do something. Thank you.
Thank you guys for this amazing talk. I feel really inspired to break things apart in a very creative way. We have some time left for questions, so if you have questions, please line up at the microphones. But first, we are going to start with a question from the internet.
Thank you. I proxy 2 related questions from the internet. First one, how hard did you guys laugh when Bitify announced that their Android-based wallet was unhackable? And the second question, have you ever tried to attack larger processors, like ARM-based processors?
Yeah, so maybe let's start with Bitfy. So we only talk about somewhat secure wallets. We didn't want to use a Chinese phone in this talk. So we laughed pretty hard and we ordered some, but yeah.
Yeah, and I mean, this was covered extensively. So another guy who you should follow on Twitter, Cyber Gibbons, gave a talk at hardware.io on the topic of the Bitfy. He was summarizing research that he did in conjunction with a bunch of other people as well. So if you're interested in the Bitfy, you should go look at them. So the second question was about ARM-based controllers. I mean, all of these were ARM-based. Every single chip, as far as I know, that we looked at was ARM-based in one way or another.
Yeah, and so if you're interested in this, look at glitching the Nintendo Switch, where they glitch the Tegra used in the Nintendo Switch, which is very interesting and will give a lot of inspiration in that regard, basically.
Thank you. A question from microphone 4, please.
Hi, Trezor CTO here. First, thank you for the talk. We'll be working with fixing the issues as soon as I return back to Prague. And if anyone is interested in hacking hardware wallets, please do. We are really interested in working with the wider hackers community, and we have a responsible disclosure program. You mentioned problems with supply chain attacks, but no obvious solutions. So let me give you one. Like Trezor is open source hardware, so you can build your own from locally sourced components. And if you are paranoid and don't want to deal with this kind of attacks. But my question is there any other solution except for building your own wallet or inspecting the bought one and tearing it apart, basically?
So maybe, first off, thank you. One thing we should mention is that when we looked at the Trezor code, the reason we had to end up glitching this chip for 3 months is that we couldn't break the firmware otherwise. So they do a great job, and it's really awesome.
Yeah. So, I mean, yes, the firmware on the Trezor is something to look at. I mean, I recommend that, I mean, we all do consulting work as well. And so it's something that I recommend that people who are interested in looking at how to prevent certain do mitigations in hardware, it's an excellent project to look at. And so Trezor should be commended on that. But at the end of the day, it doesn't mean that the chip that the Trezor uses is secure against these kinds of attacks. And that's where we had to fall back to looking for silicon vulnerabilities against a chip like a wallet like the Trezor.
So I would say on the supply chain side, this is a very difficult problem. Governments especially have this issue. You can do cryptographic attestation, but as we saw with the Legend Nano, that cryptographic attestation didn't help verify the device was genuine against the hardware percent. So there's been talk about X-ray reporting and all this stuff, but I think this is still a very much open problem in hardware security.
Another question from microphone 3.
Actually, I have a suggestion.
Make it short though, because usually we just take questions. One sentence.
A few MCUs actually have JTAG connected via hardware fuses.
Yep.
So this might be used to at least slow down glitching attacks. Thanks.
I agree, but these are not Cortex-M microcontrollers. I can tell you that with 100% certainty. And it has to do a lot with the fact that the microcontrollers that are being used in these devices, they're built to the spec that ARM specified, that ARM thinks would be a good set of features for this class of device, or rather for the CPUs, for the class of device that they ended up getting put in. So anything Cortex-M is going to have vulnerabilities that are more or less like the silicon vulnerabilities that we had. It's just I mean, if you ask me, I think it's a matter of time just to sit there. I mean, fortunately, we had something like 3 months of just glitching to be able to find these bugs, but if you can apply that much to find a silicon attack, you might be able to find this kind of vulnerability as well in other Cortex-M products.
I only have 3 minutes.
All good. Another question from microphone 4, please.
So obviously, as part of your work, you analyzed the firmware of these devices. Did you find that the firmware was in any way obfuscated or encrypted?
So basically, on these chips, you cannot really encrypt the firmware. On the ST31, you can encrypt it, but we didn't have to look at it because the ST31 is not something you have to break. But so, no, there was no real obfuscation that we could see. But we also don't have the code in the case of Ledger, so I just stared at IDA Pro for hours, and yeah.
The next person on microphone 4.
Hello. Did you have a look at the entropy that generates the master seed on both of these hardware devices, and what's your take on that?
I mean, so we already covered how the Trezor works. So there's only one chip, and it's the STM32. So I know that there was a known issue with Trezor back in the day where they weren't seeding basically the RNG correctly, but this was fixed. But for our attacks, this wasn't an issue. I mean, if you were concerned about how strong these are, how strong the random number generators are for creating a seed, you could actually create a BIP39 wallet outside of any one of these, and then just use them for their hardware features, and I mean, get the seed from outside.
If you have a question, do move to the microphone if you're able to. But first, we have another question from the internet.
Thank you. Did you guys see the Dinosaurier Hip Hop Zero wallet?
No, but if you send it to us, we are happy to look at the Dinosaurier. Oh, you did?
Yeah, we had it.
Thank you for the kind of framing to mention this. So the Dinosaurier Hip Hop wallet was a Trezor clone that we looked at last year to help Bitcoin board. So, I mean, it otherwise functionally is a Trezor clone, but we used a lot of the instructions from Dinosaur Hip-Hop, make the break to Bitcoin board, and then carry on.
I mean, and maybe on that note, I would say that in terms of looking at what wallets are actually being used, you'll find that, so the Ledger is a very popular wallet, the Trezor is a very popular wallet, but since the Trezor is open source, there's a lot of clones and forks of the Trezor. And when I say that, not all of them run the latest security patches that have been applied to the Trezor codebase. So that's also something that you can do, is basically diff the projects and see which ones are staying up to date and which aren't.
Your question is to be the very last one today. Please speak directly into the microphone. Even closer to the mic.
Okay. Seeing as this is the first CCC for many of us, and some of us might not have much experience in hardware hacking, do you have any tips for beginners?
Yeah, lots of them. So buy an Arduino, learn what mistakes you do with it, and learn how hardware works, basically. Watch a lot of online videos, and I think you gave presentations, I gave some presentations, so just watch talks, watch Live Overflow, great YouTube channel on exactly this stuff, and yeah. And also, don't hesitate to reach out to us. If you have a question, always contact us, info@walletfail, on Twitter, wherever. We are happy to talk to you. It might take a while, but yeah.
On non-security electronics, if you go to SparkFun or Adafruit, they have lots of free material on just how electronics work, how to get started. It's not security related, but it's very, very electronics.
But I'll say I started with Arduino too. I mean, even me.
All right, thank you guys so much for the very nice questions, and you guys for the amazing and inspiring talk. Thank you so much.